So this is the third part of the presentation. I skipped some parts in the module for the video discussion because we can just read it. Anyway, we will not be dwelling more on the computation and that part. So I'll be focusing more on this part. So these are the learning outcomes of the said unit. This will be linear regression. So what is linear regression? It is a basic commonly used type of predictive analysis. When you say predictive analysis, it's a way of predicting something in the future. So if you have these number of people today, how many people will there be in the future? So two areas that regression wish to examine are, so the first question would be, is it possible to forecast an outcome variable using a number of predictor variables? And what variables are the most important predictors of the outcome variable, and how do they affect the outcome variable? So let's say, for example, in the COVID cases now, so what are the variables that we need to look into? Would it be the number of people who die? Will it be the number of people who um, have recovered from the disease, or is it the number of new cases every day? So, which among the variables would be the most important, so that we will know how it will affect the outcome. So, regression analysis is used in determining the strength, how strong the predictors are, uh, forecasting an effect, and trend forecasting. So if you can remember at the start of the pandemic, there are a lot of reports on predicting that in by this month there will be this number of people will be uh, affected or infected by the virus. So how do these people predicted the number of people who will be infected? So the regression equation, which explains the amount of variations observable in the independent variable x. So we have the independent variable x is as follows. So it's just a simple linear equation. That's why it's called linear regression. Linear regression. So y equals a plus b times x. So where y is our criterion measure. So that would be the the dependent variable. So it will depend on what will be the values on the left side or on the right side of the equation. So x will be the predictor. A would be the ordinate or the point where the regression line crosses the y-axis. So that is the y-intercept, right? Yeah, the y-intercept. And B is the beta weight or the slope of the lines. Remember your linear equation, you have y equals mx plus b. So this is actually, how do you call it? Mm, an application of the linear equation. So this will be our formula. So we have to know what A means and what B means. So you might be having headache looking at the symbols. So these are just very simple symbols. So we need to learn how to read them and how to interpret them. So our A, which is our as we said, that's our y-intercept. So our A, if we're going to solve it, that would be the summation. When you say summation, that is the total, the sum. Summation of the y times the summation of the square of x minus the summation of x times the summation of x times y all over n here represents the total number of values, times the summation of the square of x minus the square of the summation of x. So that will be our A. So our B is equal to n, that is our total number of data or values, times the summation of the product of x and y minus the summation of x times the summation of y, all over n times the summation of the square of x minus the square of the summation of x. So there's a difference between this part here, which is the summation of x squared, and the square of the summation of x. So since we have it enclosed in a parenthesis, we read first the one outside the parenthesis. So example, this is the example written in or reflected in the module. So the data represents the members of the TGIM organization for the last 4 years. So we can refer this as a school organization. Predict the number of members 6 years from now. So we assume that the number of members is increasing. So our x here would be the number of years. So year 1, 2, 3, and 4. While our y is represents the number of members in the organization. So year 1 we have 16. Year 2 we have 21, and year 3 we have 25. Year 4 we have 30. So for our solution, it's good to uh, create a table so that it would be easier for us to substitute the given values. So we just add the additional columns so that we can get our we can just simply substitute our values. So we have the first column, we just have it as is. We just have to add all the values. So we got already our summation of x, which is equal to 10. So we have now our summation of x, while our y, please recheck if I have solved it correctly. That is the summation of y is equal to 92, and we get the square of x. So the square of x, this is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and we add everything. That gives us the summation of x squared is 30. Well, our last column will be our x and times y. So we just simply multiply our x with our y. So that's 16, this is 42, that's 75, this is 120. And we add all the data here, and that gives us 253. So the summation of x squared, or the total of, xy, x times y, is 253. So moving on, we will be applying now the formula. We start with the formula for A, and then we solve for the B. Before we will be using the linear regression equation, which is this one. Okay, so we now apply for our A. So the summation of y, we get it from here. That gives us 92. So check, that's 92. Summation of x squared, that is 30. So we have 30 here, minus summation of x, that is 10. So we have 10 here, and times the summation of xy, that gives us 253. So all over, there are 4 values here, so that will give us 4 times the summation of x squared, that's 30, so we have 30 here, minus the square, so we square, of the summation of x is 10, so we square 10. So applying MDAS here, that will give us 92 times 30 minus the product of 10 times 253. While the denominator, we get the product of 4 and 30. After that, we subtract it with 10 squared, which is 100. So after solving, we have 230 over 20, and that gives us 11 over 15. So our A now is 11 over 15. Moving on to the B formula, so we start with n is 4, the summation of xy. So look for the summation of xy, that is 253, minus summation of x, that is 10, summation of y, that's 92, all over 4, which that's our n, summation of x squared, that is 30, minus our square of x, and that is 10. So that gives us 10 squared. So upon solving, we got b equals 92 over, I missed to include 20 in our module. So that's 92 over 20, and that gives us a result of 4.6. So our B now is 4.6. So we now substitute the value of the solved A and B in our linear regression formula, which is y equals a plus bx. So our A here is 11.15, and our B is 4.6, and our x here is 6. So that will so the x there represents the number of years from now, so 6 years from now. So that's multiplied by 6, so 4.6. Applying the MDES formula, we multiply 4.6 by 6 first before adding to 11.5, and that gives us 39.1. So since we are talking about people here, we cannot have a 0.1 person. So we are going to round off to the nearest whole number. So there could be. So we cannot say that there will there. We cannot conclude that the exact number, because it's just a prediction. So there could be around 39 TGIM organization members 6 years from now. So we assume that the numbers will increase and there will be more people by then. So it's not that much from in 4 years. There will be just an increase of 9 people from here. Okay, so this will be for the example. So for the correlation, it's just reflected in your module. When greater values of one variable consistently go with greater values of another, or when higher values of one variable consistently go with smaller values of another, there is a correlation between the two variables. So we have to take note that they go hand in hand. One value go with another value. So take note of the pattern. So examples of correlation. There is a correlation between variables height and weight for people. So people who are taller appear to weigh more than those who are shorter. So it's just assuming, because it states here the word appear. So tall people may be heavier than those who are shorter, but it doesn't uh, not all the time, right? But there is a correlation. There's a correlation between the variables of the demand for face masks. So nowadays we are required to wear face masks when we go outside, and the price of face masks. So during the peak of pandemic, there was a shortage of face masks, of alcohol, and so many things. So the demand of face masks, because there is a shortage of production, and there was a hoarding going on. So the price of the face mask also increased. So the demand of face mask tends to decrease as price increase. But if there is uh, there are more production already, then it will go down also. Um, but we have also to remember, if you were watching the news, the government asked the Department of Trade and Industry to control the prices of these things that we are actually buying. So there must be a ceiling as to the price of these things. Volleyball players have made a correlation between practice time and ability. So, volleyball players who practice more tend to be more skilled. So, if you are a volleyball player and you are practicing less, that would mean that your ability to play in the court, on the court, will not be as good as those who practice regularly. So types of correlation, there is no correlation when there appears to be between the two variables. So there appears to be no correlation, of course, and all factors are found to rise or fall in sync. That's positive correlation, and the two factors appear to shift in opposite directions, with one rising and the other dropping. While the strength of correlation, the better the correlation between two variables, the closer they adapt the general pattern, either positive or negative. A straight line links all of the data points. So straight line. Possible explanation for a correlation. It's possible that the correlation is merely coincidental. A particular underlying factor could have a direct effect on both variables, and it's possible that one of the correlated variables is the origin of the other, and even in this situation, it's likely that we've just discovered one of the options. So, causality determination guidelines to examine whether a suspected cause really has an impact. We do the following. First, we look for uh, cases where the result is correlated to the suspicious source despite the presence of other variables. And verified effect is equally present or absent among groups that differ only in the presence or absence of the hypothesized source. We look for proof that higher concentrations of the alleged cause result in higher concentrations of the reaction. If you believe the impact could be triggered by anything other than the alleged source, double check that it still exists after you've excluded these possibilities. If possible, perform an experiment to validate the hypothesized cause. If doing the experiment with humans is not feasible due to ethical consideration, try using rodents. Rodents meaning the rats, cell cultures, or machine models. Try to figure out what physical process the suspected sources uses to trigger the reaction. So we can actually make use of this. Of course, for professionals, they are applying this one. But for now, we will just be focusing on the concepts, since we cannot. It's very difficult to apply this virtually. Okay, so I think this is one more. Okay. This will be the last slide. I have no more presentation on the last slide. So that would be all. If you have some questions and clarifications, please drop your comments below. Thank you so much for watching.